Imagine being pinned to a ceiling by a radioactive metal rod, so contaminated that rescue teams can only spend 65 seconds in the room before risking lethal radiation exposure. Your body is so hot with radiation that approaching you means certain death. And you're going to stay there for a week because pulling you down might trigger a second nuclear explosion. This actually happened to a 26-year-old Navy electrician in Idaho in 1961. And it's the most gruesome nuclear accident in United States history. What started as a routine 4-inch adjustment turned into a 20,000 megawatt nightmare in 4 milliseconds. If you're fascinated by the engineering disasters that change how we build our world, hit that subscribe button because we're breaking down the moments where small mistakes had catastrophic consequences. January 3rd, 1961. Emergency responders are dispatched to the SL-1 reactor after heat sensors triggered an alarm at 9:01 p.m. They'd already responded to 2 false alarms earlier that day, expecting this one to be the same. They have no idea they're about to walk into something that will haunt nuclear safety protocols forever. After the Christmas holidays, Army Specialist Richard Leroy McKinley, John A. Burns, and Navy Seabee construction electrician Richard C. Legg began restarting the SL-1 nuclear reactor at the National Reactor Testing Station near Idaho Falls, which had been taken offline for the holidays. The most important part of this procedure required manually lifting the central control rod just 4 inches to reconnect it to its drive mechanism before SL-1 could start producing power again. As Burns reached down to lift the 84-pound rod with his bare hands, Legg, who was the shift supervisor, stood beside him on top of the 9-foot reactor while trainee McKinley observed close by. The 3 young technicians had no idea a reactor designed to produce 3 megawatts of thermal power was about to surge to nearly 20 gigawatts in just 4 milliseconds, turning their simple task into something far more horrifying. A surge of almost 7,000 times the reactor's design power should have been impossible, but the stationary low-power reactor number 1, or SL-1, wasn't an ordinary reactor. It was an experimental military design developed on a crash timeline for remote Cold War radar stations across North America's most isolated regions, part of early warning systems against Soviet bombers. Supplying these sites with power proved nearly impossible. They were cut off from power grids, isolated from transport links, and subject to extreme cold during winter. Rather than abandoning the program, the military contracted nuclear specialists at Argonne National Laboratory to design SL-1, an easy-to-transport, small-scale boiling water reactor that allowed stations to generate heat and electricity entirely on their own, but its practical design created deadly vulnerabilities. For the reactor to run for years without refueling, engineers loaded SL-1 with 14 kilograms, about 30 pounds, of highly enriched 93% uranium-235. That amount of concentrated uranium was higher than what sat inside the Hiroshima bomb, making SL-1's core so sensitive that even small movements of its control rods caused sudden, dangerous spikes in power. To address this, engineers introduced thin boron aluminum burnable poison strips inside the reactor core. These strips absorbed excess neutrons, which slowed the rate of nuclear fission and theoretically would prevent sudden power spikes while helping the reactor operate safely for longer. However, this was a new and untested idea. Over time, extreme heat and corrosion could cause pieces of boron to break off and slip into narrow gaps around the fuel, jamming the channels the control rods had to move through. Unfortunately for the 3 men, this is exactly what started happening. Between February 1959 and December 1960, SL-1's control rods jammed over 80 times. Unlike commercial reactors sealed inside thick concrete containment structures, SL-1 operated inside a thin steel-walled building called ARA 602, whose unsealed outer shell was intended mainly to keep out the weather and serve as part of the cooling system, not to contain an accident. Instead of having permanent shielding made of thick, dense materials to absorb deadly gamma rays and high-energy neutrons around the radioactive core, the men had only a few movable lead blocks for protection and often stood just a few feet away from the small 4x4 foot reactor. With so little shielding, their radiation exposure near the vessel exceeded a modern worker's entire annual safety limit in just minutes. With dose rates reaching 200 to 500 millisieverts per hour, they were being exposed to more than 100,000 times the hourly background radiation most people ever receive. Despite building a facility that pushed the limits of safety, officials went ahead with their plan to use ordinary recruits to operate SL-1. Argonne incorporated a simplified control system that could be taught in an intensive 9-month Army qualification program. As a result, SL-1 relied on just 5 cruciform control rods to manage its power output. This was highly unusual. For comparison, Chernobyl reactor number 4 used 211. The arrangement of the limited number of control rods meant that the central rod was extremely powerful. It was positioned directly above the core's highest concentration of neutrons, and if it were withdrawn just a few inches too far, it could drive the reactor into a prompt critical state with deadly consequences. No single control rod should be powerful enough to shut a reactor down or start it up all by itself. But at SL-1, everything that followed came down to that central control rod. Nuclear reactors use fuel rods, or in SL-1's case, fuel plates that contain nuclear material. These materials naturally emit particles as they decay, producing a tiny amount of heat. But when these fuel plates are brought close together, like in a nuclear reactor, the released particles react with other nearby fuel, setting off a chain reaction called nuclear fission that generates massive amounts of heat. To control this reaction, control rods are used to absorb those particles. By moving these rods up or down inside the reactor, the rate of the chain reaction and therefore the amount of heat produced can be precisely controlled. Reactors then use this heat to turn water into steam and steam into electricity. Operators at SL-1 were aware of how this worked, but it's uncertain if they were aware of just how sensitive that central rod was, since they were just ordinary technicians. This is when things became extremely dangerous. Before the holidays, SL-1 was made subcritical by fully inserting its control rods into the core. While it was technically offline, this didn't stop nuclear reactions entirely. A low level of fission still took place inside the reactor, meaning it was as vulnerable to control rod movement as it was during normal operation. As Burns began restarting the reactor, he tried to lift the central control rod number 9 from SL-1's core, but instead of the intended 4 inches, he for whatever reason yanked it 20 inches. Within 4 milliseconds, SL-1 went prompt critical. With nothing keeping fission in check, the raised control rod triggered an unstoppable chain reaction, devastating the lightweight reactor. Neutrons multiplied like wildfire as SL-1's power output surged past 20,000 megawatts. The massive burst of energy flash-boiled coolant water around the core's fuel, transforming it into superheated radioactive steam. Pressure inside the vessel instantly spiked from 20.4 atmospheres to over 650 atmospheres. As the steam expanded, a violent explosion slammed the remaining water into the top of the reactor with so much force that the 26,000-pound vessel jumped 9 feet into the air. Burns, who was right next to the reactor, was slammed against a concrete wall as SL-1 ripped apart, while metal shards catapulted in all directions, severely injuring McKinley. But the chaos wasn't over yet. The blast violently ejected the steel shield plugs from the top of the reactor, unleashing radioactive water and debris all over the 3 men and propelling one of the control rods upwards toward Richard's leg, impaling him through the groin and out his shoulder. Meanwhile, heat sensors above the reactor triggered an alarm, immediately alerting the National Reactor Testing Station Fire Department 8 miles away. The firemen had already responded to false alarms from the facility that morning and afternoon, so they expected this to be yet another one. At 9:17 p.m., when a health physicist and the assistant fire chief entered the adjacent building wearing air tanks and masks and approached the reactor building stairs, their radiation detectors jumped to 25 roentgens per hour. Unable to believe the radiation levels could be that high and suspecting their detectors were faulty, they were forced to retreat. After grabbing a higher range detector, They returned and carefully ascended the stairs, but this time, the meter maxed out at 500 Roentgens per hour. They managed a quick look into the reactor room and saw scattered debris but no sign of the missing operators. With radiation levels reaching dangerous doses within minutes, they retreated once again. It took emergency responders over an hour to plan and attempt a full entry into the reactor room. By 10:30 p.m., the lead health physicist and operations supervisor arrived on site. Halfway up the stairs, they heard faint moaning. Quickly making their way into the reactor room, they found McKinley barely alive and a second operator, Burns, with no detectable pulse. Joined by 3 more health physicists, the team returned with a stretcher and successfully evacuated McKinley. He was loaded into a panel truck, then rushed into an ambulance, but before the ambulance reached the nearby highway, McKinley was pronounced dead. The contaminated ambulance, still carrying his body, was driven into the desert and abandoned for several hours. The third operator was still missing, but recovering him would be anything but simple. After evacuating McKinley, 4 firemen entered the building at 10:38 p.m. and made their way into the reactor room, but found no sign of Legg among the destruction. It was only when one of them scanned the ceiling with a flashlight that responders realized what they thought was debris was actually Legg, impaled and pinned to the ceiling above the reactor by the number 7 shield plug. His radioactive body couldn't simply be pulled down. Doing so risked the shield plug that pinned him falling back into the open reactor core, dislodging fuel elements and triggering a second criticality event. Legg was positioned in the most radioactive part of the room, with meter readings capping at 1000 Roentgens per hour. Anyone standing directly beneath him faced a lethal dose within minutes. With no safe course of action, a team of specialists began designing the equipment needed to reach Legg and Burns without endangering rescuers. Burns' body could be removed by the next day on January 4th and taken to the same facility as McKinley for decontamination, leaving the most dangerous recovery yet. It would take almost a week before Legg's body could be reached, as engineers designed a special stretcher system suspended from a crane outside. When everything was finally ready on January 9th, small teams entered in short rotations, each spending no more than 65 seconds inside the reactor room. The plan meant they would receive non-lethal doses of radiation around 27 Roentgens, but still enough to raise their lifetime cancer risk. Using long hooked poles, they pried Legg free from the shield plug without standing beneath him, guiding his body into the suspended stretcher. The crane operator lifted him clear of the room, and Legg was taken to the same facility as the others, where all 3 men were prepared for burial in lead-lined caskets, sealed inside metal vaults and covered with concrete. Investigators could never determine exactly why the control rod was lifted more than 4 times higher than intended. The most likely cause was that a mechanical jam likely forced the men to pull harder. Whatever the reason, the 3 operators were all in their 20s, with Burns just 22. The disaster ended the Army's top-secret portable nuclear power program and transformed reactor design, leading to new safety systems, stricter training, and the one-rod rule that ensures such a tragedy can never happen. Again, today, SL-1 remains the only fatal reactor accident in American history. Now, here's a question for you. If you are redesigning the SL-1 reactor, knowing what we know now, which safety feature would you prioritize adding first? Option A, a physical mechanism that prevents any single control rod from being withdrawn far enough to cause a prompt critical reaction. Option B, thick concrete containment structure and proper radiation shielding to protect operators during normal operations. Option C, automated control rod systems that eliminate the need for manual manipulation entirely. Drop your answer in the comments, because I'm genuinely curious which engineering solution you think would have prevented this tragedy.